Hello IB students, today we'll be solving the sixth question, the Physics HL Paper 2 2024. Let's get started. Question 6. State what's meant by the half-life of a radioactive nuclide. Half-life is the time it takes for the initial number of nuclei we start with to reduce to half that amount. In fact, the equation governing radioactive decay is given by this equation: n equals n naught e to the minus lambda t, where n is the number of undecayed nuclei and 0 is the initial number of nuclei. And lambda, it's known as the decay constant. The plot of n with respect to t is an exponential plot that falls off. If you start off with n0 and not number of particles, and the time required for the initial number of particles to reduce by half, that time is called as the half-life. In fact, we can define the half-life in terms of activity. Activity tells us how many radioactive decays occur in a second. The equation for activity goes as A equals A0 e to the minus lambda t. It's exactly the same as the initial equation. So the time it takes for the initial activity to reduce by half its original amount, that time is the half-life. So you can choose any one of those to define the half-life. Okay, that solves the first part of the problem. Let's move on to the second one. Tritium, 1 proton and 2 neutrons, is a radioactive isotope of hydrogen. The activity of a sample of tritium decreases to A0 over 8 after a time of 37.0 years, where A0 is the initial activity. Calculate the half-life of tritium. Okay, so if A0 is the initial amount of tritium and we wait for one half-life, the activity is going to reduce by half. So this is the half-life. In another half-life, the activity is going to reduce by half of the original amount. That will make it A0 over 4. In another half-life, the activity is going to further reduce by a half. That will make it A0 over 8. So if we look here, it took 1, 2, 3. It took 3 half-lives to go from A0 to A0 over 8. That means 3 half-lives must equal 37.0 years. From this, we can find the half-life. Half-life would be simply 37.0 divided by 3, which is about 12.3 years. And that solves this part of the problem. Let's carry on. Deuterium, another isotope of hydrogen. It has 1 proton and 1 neutron. And tritium undergo nuclear fusion according to this reaction. Identify nuclide X. Focus on the reactants. We observe we have a proton here, proton here. So X must contain 2 protons. Okay, so let's write that down. X contains 2 protons. What about the nucleon number? The nucleon number is always conserved in a nuclear reaction. The reactants have 5 nucleons, and since neutron has 1 nucleon, so X must contain 4 of them. So the nucleon number is 4. So 3 and 2 is 5, and 4 and 1 is 5. So nucleon number is conserved. So if you look at this nuclide here, it's just a helium atom, 2 protons and 2 neutrons. So nuclide X is just a helium nucleus. You can also call this an alpha particle because helium nucleus is known as an alpha particle. And that completes this part of the problem. Let's move on to the next part of the problem. The following data are given for binding energies per nucleon. We have the binding energy for deuterium, for tritium, and for the helium nucleus. Show that the energy released in the reaction is about 18 mega electron volts. To figure out the energy released in this reaction, let's focus on X for a while. It has 4 nucleons. For every nucleon, about 7 mega electron volts of energy is released. So for 4 nucleons, the energy released is 4 times 7.074 electron volts. But wait, this element X is created when we disassemble, when we destroy both deuterium and tritium. To take out one nucleon from deuterium, we need this amount of energy, but it has 2 nucleons in it. So we need to supply twice that amount of energy. Similarly for tritium, since we have to destroy tritium to create the helium nucleus, we need 3 times the binding energy. So we have to supply 2 times this amount, 3 times this amount, and then we are going to get 4 times this amount of energy. So the net energy released therefore is minus 4 times 7.074 minus 2 times the binding energy of deuterium plus 3 times the binding energy of tritium. If we calculate this, we get a value of about 17.6, which is about 18 mega electron volts. All right, once again, how did we solve this problem? Well, we figured out how much energy is released when helium nucleus is created, minus the amount of energy required to break apart deuterium and tritium. This amount of energy is for 1 nucleon, so we multiply it with 2 because it has 2 nucleons. We need to break apart both of them. And tritium has 3, so we need to supply thrice the amount. And that gives us a net energy release of 18 mega electron volts. Let's move on to the next part of the problem. Hence, estimate the energy in joules released as a result of fusion of 1 kilogram of nuclear fuel according to this reaction. So we have an energy of about 17.6 mega electron volts. Let's convert this to joules. This will be about 17.6. Mega means 10 to the 6, and electron volt is 1.6 into 10 to the minus 19 joules. All right, this is the amount of energy released when the reactants react and produce the helium nucleus. But what's the mass of reactants required that gives us this amount of energy? To find that out, we go back to this reaction and we realize that we need about 5 nucleons. 5 nucleons to produce this reaction. That means a mass of about 5 atomic mass units, or simply 5 U. So the mass that goes into creating 17.6 mega electron volts is 5 atomic mass units. And 1 atomic mass unit is 1.661 into 10 to the minus 27 kilograms. All right, so we can figure out mass per kilogram. That's what we want. So we simply divide E with M. So we take this and divide it with this. And that gives us the amount of energy released per kilogram. If we put this into a calculator, we get a value of about 3.4 into 10 to the 14 joules per kilogram. That's a lot of energy. The specific energy of typical fossil fuels is 10 to the 7 joule per kilogram. Outlined with reference to the answer in D2, that's just the question we solved, the advantage of using nuclear fusion over fossil fuels as a source of energy. It's straightforward from this answer here. Each kilogram of nuclear fuel gives us about 10 to the 14 joules, while traditional fossil fuels, they give us about 10 to the 7 joules. So the amount of gain of energy that we get is 10 to the 14 from nuclear fuel divided by 10 to the 7 due to traditional fossil fuels. That's a number of 10 to the 7. So nuclear fuel is about 10 to the 7 times more energy dense than the traditional fossil fuels. And that explains this part of the problem. If you need more help, I tutor one-on-one classes. Feel free to reach out. The link is in the comments below. I'll see you in the next video with a detailed explanation of another question. Happy learning!